General relativity, step by step. I've been fooling around with the geodesic equations for slowly moving objects in a stationary weak gravitational field. And the equations boil down to this here. There are 4 equations here, one for each value of mu equals 0, 1, 2 and 3. So I'm going to consider mu equals 0 first. And of course if mu equals 0, that means that the coordinate x0 is equal to time, I guess, t. So what that tells me is that d2t by d tau squared equals a half eta, and then I'm substituting mu equals 0 into this, that's 0 lambda di h00 by di x lambda, summed over lambda of course, c squared dt by d tau squared. Just copying this equation up here. Okay, and eta is just the diagonal matrix that we've been using all along for Minkowski space. And so, of course, what this does is pick out the lambda term. This picks out the term lambda equals 0 because this is the only one that we're interested in. So d2t by d tau squared equals a half di h00 by di, well, x0, I guess, times c squared times dt by d tau squared. Because we're picking out the only one on this row here that's 0 is the lambda equals 0 term. So there's a I guess there's a minus sign there because I'm using this metric here. Yeah. Okay, and then we observe. I got the red pen out. And we can cancel that term there. That equals 0 because I've repeatedly used the assumption that the gravitational field is stationary and therefore it's got no time dependence. Yeah, it's got no time dependence. So that tells me that d2t by d tau squared equals 0. Now t and tau are different things. T is coordinate time. I guess this is time as measured by a distance observer who's far away from any gravitational field. And tau is proper time. Wristwatch time, I call it. Wristwatch time. Time as measured by an observer who's moving along a particular world line, a slowly moving world line in this case. So that tells me that d by d tau of dt by d tau equals 0. So that tells me that dt by d tau equals a constant. We may as well call it alpha. And so that tells me, that t equals alpha tau plus beta, where alpha and beta are constants. Now it looks like we've just got 2 different systems for measuring time. T might be in seconds and tau might be in minutes or something like that. But that's not the case. That's not what's happening here. What's happening is that we have a time dilation effect whereby wristwatch time, proper time, advances at a different rate from coordinate time. So we've got a gravitational time dilation effect here, measured by alpha, and I'll talk about that more in a subsequent screencast. But for the moment I want to observe that t is proportional to tau. We can do a little bit more work here. We can also say that d by dt equals 1 over alpha d by d tau as operators, and we'll use that in a subsequent screencast. Okay, stop there. Stop.